Okay, since it's 1 o'clock, I think we'll get started because we have quite a few slides to go through today, and we have there's 5 of us speaking, so we'll get on with things. I just wanted to lay a little bit of groundwork for the history of blood transfusion. I do have some disclosures. I've had research funding from a few companies. I chair the scientific advisory board of Mako Pharma, and I'm a member of the board of directors of a small startup company in Boston that was started by one of my former grad students, who is probably known to a few of you, Jonathan Thon. So I just wanted to give a little bit of history about blood transfusion so we can understand how far we've actually come. And it started out back in the days of Hippocrates. Hippocrates thought we had 4 humors in the body, and there was phlegm, which had to do with your lungs. There was black bile, yellow bile, and blood. And so this is just pictures from a German woodcut from 1498. The first real blood transfusion was actually performed on Pope Innocent VIII in the late 1400s, and they literally drained 3 young males and transfused all of their blood into the Pope, and he died anyway. So the next most important thing was William Harvey figuring out that blood actually circulated. So it was pumped by the heart, it went through the blood vessels, and this was a great breakthrough for people really understanding that blood could circulate. And he published his description of the circulation of blood in 1628. So that was the first time when we realized that we could probably collect blood from people without causing too much difficulty. There were a few attempts at animal transfusions, and in 1665, a British guy named Richard Lower successfully performed a dog-to-dog transfusion without killing either dog. And then in 1667, there was I think he was a little bit crazy, this Jean-Baptiste Denis guy in Paris, but he was believing that if you took the blood from an animal that was normally calm, so this is a lamb shown on the table, and you infused it into people who had mental illness, that you might be able to calm them down. So this is something you can do only once, because the second time you try to transfuse the blood of an animal into a human, there are so many antibodies present, you get a rapid hemolytic transfusion reaction, and the patient's likely to die. So he did this animal to human transfusion piece, and I think that the guy that he transfused the lamb blood into was probably so sick that he actually calmed right down. In 1829, James Blundell did really the first human-to-human transfusion, and he took blood from a patient's husband by syringe and used it to successfully transfuse the guy's wife, who was suffering from a uterine hemorrhage. And that's really the first human-to-human transfusion. One of the other really important things that happened was, we all have blood groups. We're all AB or O or AB. And what this gentleman, whose name was Karl Landsteiner, he was working in New York at the time, and he won the Nobel Prize for identifying blood groups for these ABO blood groups. And what he was doing was, in his laboratory, was essentially drawing blood from all of his laboratory staff and then mixing plasma and blood together, and really being able to figure out that there were blood groups. The other very important development was a way to keep blood from clotting. And so this is a 2-step method for transfusing citrated blood that was developed by Richard Lewison in 1928. And so he was the inventor of citrate anticoagulant. And thankfully, we still have citrate anticoagulant. It's still a major thing used in blood transfusion today. So I'm going to switch centuries. That was then and this is now. And think about, what are we really focused on with the goals of modern transfusion medicine? We want safe blood products. We don't want to harm any patients by giving them somebody else's pathogens. We want to have blood that is the highest possible quality so we can get the best efficacy from the transfusion. we absolutely need a sufficient supply. And I would just take a slight sidebar here and say, any of you who are blood donors, CBS needs you right now. Our blood stocks are down by about 40%. And that's also true in the US. So we should be thinking about donating. We want to make sure that any blood that we collect is used appropriately clinically. In other words, people are no longer giving top-up transfusions like you'd add a little bit of extra oil to your car, which was something that happened in days gone by. And we also are very focused, at least in Canadian Blood Services, on making sure that whatever we're doing is cost-effective. So I want to talk a little bit about blood product quality, and what's really the reality here is that blood component technology was developed decades ago. It's from the late 1960s, and the storage containers that we use, which are made of plastics, are really not fully biocompatible with the products that we're making. And Nicolas is going to give us a little bit of a presentation after I'm finished that talks about how he's trying to improve platelet storage containers. By blood component quality, I really am talking about this particular kind of arrangement where we have, these are normal red cells at day 1, and this is what happens after 21 days. They start to develop these echinocytic forms, and then by day 35, a lot of these cells have lysed, and you have free hemoglobin in the bag, and none of that is very good for patients. So what else is in a blood product? Narges is going to talk to us about her work on heavy metals in Canadian blood donors and what she's been finding there. We all, if you live downstream from a tailings pond, you're likely to have a higher heavy metal concentration in your blood donation than people who live in places where the water's filtered. So we do have a renewed focus on blood product quality, and it comes from several observations. First of all, there was a concern that the age of blood is an important factor in transfusion outcomes, and that old blood may actually harm patients. So if we look at the allowable storage time in North America, it's 42 days. If you go to Europe, it's 35 days. And there's very good evidence in that 6th week of storage that you have a lot of free iron in those bags. So you don't really want to get 6-week-old blood. We have new technologies such as pathogen reduction, which actually seem to lower the quality of blood products as we currently define them. And we also have started to recognize that each one of us has a certain amount of a certain way that our blood stores, and that's genetically determined. And we want to understand the role that donor factors play in product quality. So Elyn's going to talk to us about her plans to address these aspects, particularly in diabetic donors, which we now allow at CBS, and also in older donors. Here's an example of, this is work that was pulled together by the BEST Collaborative. And this is a bunch of quality control data from different blood operators around the world, including Canadian Blood Services and Héma-Québec, which are the 2 Canadian operators. And what we did was we pooled all of our quality control data together. And we asked the question, if a donor has a platelet product that fails pH at outdate on one donation, are they more likely to fail on a second donation? And as you can see from what's in this red box, all of these are failures, and that people who are failing once are likely to fail again. So we know that there's a certain genetic factor that contributes to the failure of platelet pH. So what do we really need in the research arena? What we really need are randomized clinical trial data that can really help us understand the impact of storage lesions. We need to know what causes these storage lesions to develop. We need better quality control approaches to ensure product quality, and that might include actually genotyping all of our blood donors. And we need to develop better ways to store blood products. So what's really new in transfusion? Probably not that much. This is a slide that we're learning from military trauma medicine, that whole blood works better than component therapy, that cold stored platelets are really good for bleeding patients, and Wayne's going to talk to us about cold stored platelets. And I have a project going on with the Canadian Forces looking at trying to bring back freeze-dried plasma, which would allow us to do a better job of managing our plasma inventory. So using whole blood in trauma, clotting factor levels are no worse than liquid stored plasma, and they're certainly better than clear liquids. So people in the battlefield situation had been giving crystalloid and colloid liquids, and people just get a dilutional coagulopathy out of that, which is not a good thing to have. So platelets don't remain in the circulation once they're transfused owing to this cold lesion, but they're very good at promoting clotting because they're partially activated. We're seeing an increasing use of whole blood in pre-hospital settings. And again, this is relying a little bit upon the military experience, but there's now quite a few papers in the literature that show that you can improve the survival of someone who gets in a major car accident, for example, by about 50%. They have 50% reduced risk of dying if you can get blood products to them before they arrive at the hospital. And what we really need are just really a lot more clinical data for looking at how we're managing these things in modern days. So just to mention what we're doing at Canadian Blood Services to bring whole blood to Canada, we have a submission before Health Canada at the present time. We hoped to initially support 2 clinical studies. One is a trauma project in Vancouver, where we will send whole blood out on our life flight helicopters and our fixed wing aircraft. And then there's one pre-hospital transfusion study that would be conducted out of Sunnybrook Hospital in Toronto. What we really need to understand are the use issues. We need to make sure that so it's Group O whole blood that we send out on these helicopters, and we want to make sure that it's not wasted. So we have to understand what the wastage rates look like, what the impact on Group O red cell inventory is, and other important questions like that. And the hospitals, we've asked the VGH guys, because I've been working most closely with them, to really put together an algorithm where they can ensure that they won't be wasting these whole blood units. And what they did was essentially go to the emergency department and say, look, you got people coming in with trauma. We want to use these whole blood units there. So that's what's happening locally. Wayne's going to talk to you about cold stored platelets, which has been his thesis work. And I just wanted to say that blood transfusion is really a highly interdisciplinary field with a broad societal impact. And just to acknowledge a whole bunch of folks who've been working with us, and our collaborators, mostly Angelo D'Alessandro has been doing a lot of our metabolomics and proteomics work. Bill Sheffield is our plasma protein guru. Andrew Beckett is my Canadian Forces colleague, he's a trauma surgeon at St. Mike's Hospital. And then Jay and Christian Kastrup have been important collaborators within the CBR, and we're funded by that collection of funding sources listed there. So I'm going to turn this over to Nick.
Everyone can hear me okay, right? Yeah, beautiful. Okay. So my project concerns developing new storage devices for platelets that hopefully extend their shelf life. And before I go any further, I really want to acknowledge the contribution of Jay Kizakadatu, Kai Yu, and Helen Chen. This is not at all only my work. They are absolutely so helpful, and it's a pleasure working with them. So as hopefully most of you know, platelets are those little cells in your blood that are responsible for making it clot. Blood vessels get damaged and platelets get recruited to the site of injury, where they plug up the hole and then participate in coagulation, building that big old blood clot that holds the endothelium and allows it to heal. Now, Platelets in medicine are used for their transfusion, like we've just been talking about. Platelet transfusions are done in, broadly speaking, two different contexts. The first of which is people that are actively bleeding out. So on the operating table, car accident, battlefield injury, that kind of thing. And the other major pool of recipients is people that have a platelet deficiency, namely chemo patients. Chemo destroys blood cells, so these people are at risk of internal hemorrhaging from a deficit in platelets. So we transfuse platelets prophylactically to try and address that problem. This is all fine and dandy, but the one core problem is that platelets are unbelievably difficult to store. The instant that you take platelets out of circulation and put them into storage, they experience a dramatic decrease in every measurable quality that they have. They clot less effectively. They are cleared by the body more rapidly. The outcome of the transfusion is not as good. And importantly, the shelf life of the cells is really, really hurt. In circulation, platelets live like 9, 10-ish days. But in storage, they live more like 6. And most places only license them for up to 5 days of storage. This whole loss in quality and the decrease in lifespan is called the platelet storage lesion, and it is one of the biggest problems that blood banking in general has to deal with. It's an enormous issue. Almost a third of platelet products that get manufactured in Canada end up in the garbage. A third of them. And we have pretty good stats because CBS is really good at their job. Most countries have staggering platelet waste statistics. And we don't deal with platelet shortages as much. Recently now with COVID, absolutely, but platelet shortages is something most healthcare systems routinely have to deal with. So addressing this storage lesion, finding a way to get platelets to live longer, to protect their quality is absolutely central to improving transfusion medicine and blood banking. So why does the storage lesion actually happen? One of the core reasons is, as Dana was saying, the storage devices we have are just not that good at their job. They're made of a material called polyvinyl chloride. We use it because it's oxygen permeable, so the cells can breathe, but it's super hydrophobic. Platelets love the hydrophobic surface. They stick to it, they get activated. Activated platelets go on to activate other platelets, and so on and so on. And you get this massive positive feedback loop of platelet activation. The oxygen level decreases, the glucose levels decrease, the pH decreases, and all of this results in the destruction of the whole transfusion product. So the theory behind the project is, well, okay, if the material is one of the core problems, then what you could hypothetically do is develop a coating. Super hydrophilic. It sits at the interface between the platelets and the bag itself. Super hydrophilic prevents the hydrophobic interactions. Hopefully we protect the cells from the damaging interactions, extend their shelf life, protect their viability. And that's really the rationale behind the project. We are in the middle of a little pilot study where we're testing our first polymer composition, and the rest of the presentation is really me showing you the results that we've actually collected so far. In terms of my workflow, this is brief, just so you guys understand what I do. I get my platelets from CBS and I put them into either the coated bags or the uncoated bags. And then every couple of days throughout the storage period, which is up to 2 weeks, I measure 3 key platelet health parameters, essentially. The first of which is the platelet activation. This is what we want to know, right? Are the platelets in the coated bags more or less activated than the uncoated ones? The second of which is their metabolism. I want to make sure my platelets are happy. They have enough glucose, the pH is in the normal range, that they're breathing properly. And then lastly, I check on their ability to clot, because that's why we transfuse them. And if they don't clot properly, then all of this was for nothing. So going into it, to measure platelet activation, what I do is I measure display of P-selectin. This is just an integrin that the platelets show only when they're activated. So activated platelets release all this stuff, one of which is this surface integrin, and I just tag it with a fluorescent antibody to measure what fraction of my cells have been activated. And just as a general convention for my results, this is going to work across the board. X-axis is always days in storage. Y-axis is going to be my dependent, it changes. And then red is coated, platelets coated bags, blue uncoated, and then circles and triangles are just biological duplicates. All we care about is the red versus the blue. And what did we see? They're extremely comparable. They seem to follow the exact same trend line. Up to day 9, they are effectively the same. And there are slight deviations after day 9, which is really past the platelet's normal lifespan anyway. But in terms of activating the cells, it did seem like they are very much comparable, and we were pretty happy with that outcome, especially for a first try. And the other thing that I do to measure activation and really cell death is I measure the display of phosphatidylserine. For those of you that don't know, cells display phosphatidylserine when they're dying. Platelets also do it when they're activating. So there's kind of two sources. But by measuring it, I can infer more or less how my platelets are doing if they're activated and they're dying. And what did we see? Again, up to day 9, the coating and the uncoated bags perform exactly the same. They follow the exact same trends. After day 9, which is, again, past the cell's normal lifespan anyway, the coated platelets did appear to be dying or were at least more activated, which is a really weird result. You would think that we'd see that difference earlier, but apparently not. So it's not exactly clear why this is happening. But for the storage period that is relevant for these cells, we were pretty happy with the outcome, even if afterwards there is a little bit of funny business. But as it were, the platelet activation, reasonably successful. It is as good as the coated bag, so we were pretty happy with that, at least for a first try. Next is the blood gas analysis. This is pretty straightforward. Again, very, very comparable. As of day 9, the glucose does get relatively low, so the platelets have to convert to doing more glycolysis. pH drops a little lower because they're producing more lactic acid. But by and large, again, up to day 9, the platelets are very happy. Doesn't seem to be any worse than the uncoated bags. And this strange business with the oxygen, you might have noticed this trend of the increasing O2. The platelets that have to convert to glycolysis end up consuming less oxygen. So you have more O2 partitioning from the atmosphere into the bag. That's why it increases more rapidly as of like day 10 to 14. But up until that point, again, very comparable. And we were pretty happy with that. And then lastly, in terms of their clotting, just because obviously that's why we transfuse them, to measure this, I use a technique called rotational thromboelastometry. You put your platelets in a cup and you activate them, it goes in the cup and it just measures resistance formed by the clot. And it tells you more or less everything you want to know. For these results, the maximum clot firmness, so how big the clot actually gets, how robust it is, extremely comparable. The coating does not seem to compromise the platelet's ability to coagulate, which was very nice. And the formation time, again, after day 9, there is some fishy business, but it doesn't seem to impact them in the biologically relevant lifespan. So while, again, strange, perhaps not as relevant. And ultimately, to wrap up, I do want to emphasize what Dana said is please go transfuse, please go donate platelets. Blood drives are really platelet drives because they live 6 days. So it's a nightmare to try and manage that logistics to get an adequate platelet supply. So every donation does count. We want to fix it by fixing the bags as one of the core ways we could possibly address the problem. We have other plans for it, though, to have antimicrobial performance, try and optimize it for path activation techniques, which is something Dana was talking about. And we have a lot of directions we can take it. So I'm looking forward to following through on this project. And lastly, again, Jay, Kai, and Helen, absolute pleasure working with them. Brana, Elena, Wayne taught me everything I know. So thank you to you guys. And that is it.
Yeah. Okay. Sorry. So lead neurotoxic. This is a slide by CDC about the adverse effect of lead on neural development. And there is no known threshold for this effect. So the recommendation is to lower the exposure to lead to as low as possible. Blood transfusion can be a source of exposure to lead if the unit comes from a donor with high levels of lead. And this is probably doesn't matter for adult transfusion, but it can become a significant source of exposure for neonates who have low birth weight or they are premature. And blood donation is not uncommon for this group of infants, and their brain undergo lots of development outside of the natural environment of home. And also lead is in constant competition with calcium, iron, and zinc in their vital roles. And these group of recipients are iron deficient. And the thing is that our body cannot clear lead, so it just accumulates and it stays in equilibrium between blood, bone, and soft tissues.
So we were interested, we were curious about the levels of lead in the donor population in Canada. We collected samples, 2,500 from all across Canada in EDTA vacuum containers. They were shipped to CBR and we measured them using mass spec in CBR. We sampled all permanent clinics across Canada and also some mobile clinics. And also we oversampled some of them. For oversampling, we thought about what are the risk factors. So you see on the right, the sources of exposure to lead. Fortunately, paint, toys, furniture are all well regulated nowadays, but still we have lead pipes, we have lead mines and smelters. Also, there are publications that show that immigrants from South Asian countries have higher lead levels. So we consider these factors in targeted sampling. So now the results. This is the levels of lead, blood lead level, BLL. You can see the range, geometric mean, and the percentile. On the right, I'll focus on the samples, number of the samples above thresholds. So we had one samples above 10 microgram per deciliter, which is the Health Canada intervention level. We had 16 samples above 5, the reference level for investigation by CDC, and we had 55 samples above 3.1. This is the level published in literature as the safe threshold for neonatal transfusion. What were the predictors for blood lead level? Sex. Male donors have higher levels of lead compared to female donors. Age, there is a significant correlation between age and blood lead level. And donor age explained 18% of the variation in blood lead level. Also, it matters where the sample came from. We have no collection centers for blood in the northern provinces and territories. So in this table, you see from West Coast to East Coast, from top to bottom, each province and the clinics in front of them. And then the lines from left to right shows the geometric mean, and then the safe neonatal threshold, 5 the CDC threshold, and 10 is the Health Canada threshold. And there is some significant difference among the locations. So the red centers had significantly higher lead levels compared to the blue centers. And it was interesting to see that 3 of the centers among these 8, top 1, were within 80 kilometers from the 2 lead producing mines of Canada. 2 other centers had large automobile and metal shredders in the cities, but we are not sure if it was the contributing factors or not. So all centers included, clinic name or location also contributed significantly to blood lead level. So now we move to mercury, another neurotoxicant. The source of exposure, you know, it is eating fish. So we use ethnicity as a guide for oversampling. And similar to lead, there has been publications that showed that there is a correlation between the post-transfusion mercury levels and the amount delivered by the packed red cells in low birth weight infants. Good news is that our body can get rid of mercury, but the bad thing is that again in premature infants, they have low metabolism and excretory ability, so the mercury can overload actually. This is the result for mercury. You can see again the range, geometric mean and percentile. And then we had one sample above 20, the maximum acceptable level in blood for adults by Health Canada. And we had 11 samples above 9.5, which is the estimated safe threshold for neonatal transfusion. And we had like 23 samples above 8, and this is 8 is again the maximum acceptable level by Health Canada, but for children, pregnant women, and women of childbearing age, that we had 5 of these donors were women of childbearing age in this table. Predictors, sex was not a predictor. There was no significant difference between male versus female mercury level. There was a significant correlation between the mercury level and age, but it was not as strong for lead. And you can see in this table that it is driven by the youngest group of the donors that had the lowest level of mercury. And again, the location mattered. Compared to lead, we had more variation among centers. The red centers had significantly higher levels of mercury compared to the blue centers. And it was notable to see that 5 out of 6 Pereyra clinics had significantly lower mercury levels than at least one British Columbia clinic. And also when we listed all our samples from the top mercury to the lowest level of mercury, 7 out of top 10 were from Metro Vancouver and Toronto. So all clinics included. Again, clinic location was a significant contributor to mercury levels. So the take-home message from this study is in that our sample size, 2,500, we observed some donations that had higher levels from the levels that are known as safe neonatal transfusion threshold. So we recommend that we can look at the blood transfusion as a source of exposure to heavy metals. And we think about informed selection of blood units for neonatal transfusion by, for example, thinking about the donor age cutoffs or the clinic location. And in the end, I would like to thank Dr. Devine for giving me the opportunity of working on this project, and the lab members. I worked with Catherine, Elena, Zhao, Brianna, and Nobu in the setting of everything, and Paris and Marcus, our lab volunteers, helped us throughout the study. And our collaborators were Dr. Murphy and Thomas and Angela. They gave us the ICP-MS, the training. Dr. Barkastas in Children's Hospital, we did the validation of our method and preparation, everything against their lab, and sample collection from Brampton and Calgary Testing Center. Dr. Chilangi, consulting on the statistics, and funding from Canadian Blood Services. Thank you so much for your attention.
Me? Okay, I'm amplified. Fantastic. Okay, so my name is Elyn Rowe, and I am a PhD student that just joined Dana's lab. And today I'll talk a little bit about the plans for my project called The Impact of Donor Characteristics on Blood Product Quality. So as we've emphasized a lot so far in this presentation, Canada needs to increase its blood supply. As with everything else, really, the COVID-19 pandemic has really affected Canada's blood supply, as Dana has mentioned. And there's actually been an estimated 31,000 donors that we've lost throughout the pandemic. So it's more important now than ever to increase this blood supply. And when we layer on the fact that we're dealing with an aging population, and with that an increased demand for blood products, you can see how this might become problematic. Dana also mentioned that we have new technologies coming down the pipeline, including pathogen inactivation, which stands to increase the safety of the products. But with that, we also see potentially decreased blood product quality, which might mean that transfusion recipients need more products than they once did to achieve the same results. And Nick discussed his project, which is really important to extend the shelf life of blood products to increase the supply. But another avenue that Canadian Blood Services is exploring, and that is important, is expanding donor eligibility. So expanding the pool of people that we can draw from to donate blood. And there's actually been a lot of work done by Canadian Blood Services over the past decade or so on this front. So as of 2016, there's no upper age limit to donate blood in Canada as long as you're healthy. This isn't the case worldwide. Most countries kind of cap it at 65. Also, we allow donors with diabetes or individuals with diabetes to come donate. So for a while now, we've allowed type 2 diabetics to donate as long as they're in good general health. And as of last March, we also allow individuals with type 1 diabetes, so those treated with insulin, to donate as well. And while this eligibility criteria includes a lot of safeguards to protect donors and recipients, most research to inform donor eligibility decision-making has really focused on the safety of the donors. So whether or not these donors may experience an adverse reaction to donating. And there's really been less of a focus on the variability in the quality of the blood products that they're donating. So what are these different blood products? We've been mentioning them throughout the presentation, and you probably pieced this all together, but when I was first introduced to the field of transfusion medicine, this was one of the most important things that allowed me to really conceptualize what was going on. So we'll just do a quick breakdown, probably review for everyone here, but most donors come in and donate whole blood, which gets centrifuged to separate it into the different components, which are platelets, the buffy coat, which contains the leukocytes and platelets, and the erythrocytes. And then plasma gets siphoned off from the top of the bag to make the product fresh frozen plasma, which is used in cases of severe trauma or active bleeding, also in burns or people with bleeding disorders who lack certain clotting factors. And since this is a frozen product, it has quite a long shelf life of about a year. Nick has done a great job summarizing everything you need to know about platelets, really, but I'll just add here that typically we have a pooled platelet product, and these are made from buffy coats of 4 different donors, which are combined with a plasma unit. Then this is leukoreduced to get rid of the white cells, so you're left with a pooled platelet product. And as Nick mentioned, this has a pretty short shelf life of about 7 days. Then you also have the red cell concentrate, so you siphon off the red cells, leukoreduce them, add them to an additive solution, and you get your red cell concentrate, which has applications also in trauma, surgeries, anemia, and different red cell disorders, and a longer shelf life. There are also some nuances. There are some other ways to donate blood which can produce different products, but these are the main products that you need to know about. So why do we care about variability in product quality? I think the easiest way to conceptualize this is that it's just generally important that we understand what's in the bag, like what is in each blood bag. And as we expand donor eligibility and allow people from different groups to donate, this is even more important that we understand what we're working with. Because blood products aren't standardized like many drugs used in medicine, and it's just important that we know what we're working with. For example, are the red cells capable of carrying oxygen still? Are they deformable enough to get into even the smallest capillaries? Are the platelets super activated? We really just need to know what we're working with so that we can best apply these products to the patients. Also, understanding where variability comes from can also enable us to tailor storage times of products. So products from some donors might not have as long of a shelf life as others, and it's really important that we understand this variability and these nuances to ensure the safe storage and use of these products. And I think this work can also inform on potential recommendations of Canadian Blood Services that they could provide to donors on which products they should donate. So for example, donors from some groups may have poor red cells but really great platelets, so we could recommend that they donate through apheresis where we get their platelet product. This also might open the door to tailored applications of blood products, which you'll hear more about from Wayne. In this case, I could see that donors with potentially really activated platelets may make great platelet products for individuals who are actively bleeding, whereas these might not be as effective in prophylactic platelet treatments like Nick has discussed. So as Dana alluded to, and you probably could have guessed from the emphasis on my first slide, the donor characteristics that I'm most interested in are age and diabetes. And I'll reiterate here that there are 2 main types of diabetes, type 1 and type 2, which have differences in their etiology, their presentation, and their treatment, but really they fall under the same umbrella of diabetes, which is defined by poor or lack of glycemic control. And interestingly, mounting evidence has shown that there are overlapping processes that happen in aging and both types of diabetes, which include changes in the inflammatory profile, altered hemostasis, increased oxidative stress, and metabolic dysfunction, which I'm sure everyone can piece together that this puts significant stress on the cells in the body. And it may follow then that these processes may affect the quality of the donated products. So they may feed into potentially red cells having increased hemolysis, decreased deformability and oxygen carrying capacity. Platelets might have higher baseline activation, and with that increased microparticle release and worse storage performance. And we may see differences in components of the plasma that could affect the individual receiving the product or could affect the pooled platelet product that it's added to. So all of these possibilities could really affect the efficacy of the products and transfusion outcomes. So it's important that we do some investigation here to really figure out what's in the bags that are coming from these different donors. And that's where my project slots in. So the overarching research question is really, how do donor characteristics, specifically age and diabetic status, affect blood product quality at baseline and throughout storage? And how might this translate to transfusion recipient outcomes? And in AIM-1, the plan is to screen for glycemic control in Canadian Blood Services donors and investigate its association with platelet activation and hemolysis as general quality markers. AIM-2 will do a deeper dive and do a full characterization of blood products from donors across the eligible age range and from diabetic donors as well. In AIM-3, I'm hoping to extend my in vitro findings to achieve some clinical relevance and investigate transfusion recipient outcomes using hospital records. So looking at tracking products from certain groups of donors and how the people who receive those products fare. But for today, I'll just focus on AIMs 1 and 2. So for AIM-1, I'm going to leverage retention samples, as Narges did in her study on heavy metals. And retention samples are really just tubes of whole blood collected at each donation, mainly used for quality control testing. They collect a few extras in case something goes wrong. So we can actually shunt these extras to our lab to do some research. And I've shown here that hemoglobin, which is the oxygen carrier in red cells, when blood sugar levels are high or when there's poor glycemic control, hemoglobin could get glycated. So sugars get attached to it. And that produces this marker, hemoglobin A1C, which is really a marker of average blood sugar levels. And this is used to diagnose, as part of the diagnosis and to monitor diabetes and glycemic control. And this is really important because we think that people with worse glycemic control may have different qualities in their products, that the quality of the product may associate with the glycemic control. So we're interested in investigating this. So basically what's going to happen is we'll flag donors with type 1, type 2 diabetes and some controls across Canada. We'll receive their retention samples, quantify hemoglobin A1C, and screen for hemolysis and platelet activation as markers of quality. And this will really inform us on the control of the diabetes in the Canadian Blood Services donor population. We can also estimate the prevalence of unreported diabetes in Canadian Blood Services donors, which is important to know, and really look at associations between glycemic control, diabetic status, and age with markers of product quality. In AIM-2, we're going to do a deeper dive and do a more in-depth characterization of these products by recruiting donors to come donate whole blood at the NetCAD Blood for Research facility. So we'll sample across the age range from individuals with type 1 diabetes and type 2 diabetes. And NetCAD staff will process these whole blood products into their components. And then I will characterize these at baseline and throughout storage using a battery of assays, as has been described by Nick for the platelets at least, to look at standard quality measures of the products. And I'll also probe into metabolism, oxidative stress, inflammation, and hemostasis to really provide some insight into the impact of age and diabetes on product quality and the underlying processes that may impact quality. This will also allow us to determine whether there's variability in the storage performance of products from these different donors, and will pave the way for a lot of future follow-up studies. So I'm in very early stages of this project, but to get this project rolling, I've got a few things on the go. I'm currently on the ethics grind, so trying to get this project through UBC clinical ethics and also Canadian Blood Services ethics. So there's a lot of back and forth going on there. I'm also working up some assays in the lab. So right now I'm trying to establish a method to detect microparticles released by endothelial cells in plasma. And this flow cytometry assay will be one of the assays that I apply to my characterization of the products in AIM-2. So I'm doing some troubleshooting with that, learning a lot about flow. And I've also done a bit of work assessing the feasibility of the retention sample screen. So as I mentioned, retention samples are collected in EDTA tubes, and EDTA is an anticoagulant that can really activate platelets. And we also might not get retention samples right away. They could be sitting around for a few days before we get them. So I just wanted to know whether the normal baseline measures of platelet activation, which we would do in whole blood with a sodium citrate anticoagulant, if we could still resolve those donor differences in these older tubes stored in EDTA. And while the baseline activation is a lot higher, you can see on the y-axis here, when they were stored over 5 days in EDTA, the measures still correlate pretty well. So I think we will still be able to resolve some of the donor differences using this screen. And we're also, I'm working with NetCAD to establish a method for single donor platelet products. So as I mentioned, the standard is to pool 4 Buffy coats together to make a pooled platelet product, but we're interested in individual differences. So we're just doing some troubleshooting, finding some smaller bags and so on to make these products. And really to wrap up here, I've already touched on this throughout the presentation, but just to reiterate, while the project is still in very early stages, we're working to position it to translate into policy change at Canadian Blood Services with the possibilities of tailored storage time, tailored applications, and potential donor recommendations. And I think we'll also gain a lot of insight about diabetes and aging along the way, which I'm pretty excited about. So thank you, everyone, and I'll pass it off to Wayne.
Work if I put it in the pocket. Thank you. Can you hear me? Okay. Okay. So first of all, I'd like to thank my colleagues for giving me enough time to finish my talk. They've done a great job in introducing all of the things I was going to introduce. So I'm very happy about that. So my name is Wayne. I'm a PhD candidate with Dr. Dana Devine. I've been working with Dana for 5 years now, actually. So today I'll be talking to you about an in vitro transfusion model to assess cold store platelets in trauma. So I would like to start off with giving you some background on platelet storage history, specifically with regards to cold store platelets. So back in the late 1960s, when we were developing our component storage therapy, all of our platelets prior to this were actually stored at 4 degrees. So these were known as cold store platelets back then. However, when we use these platelets for prophylactic transfusions, these cold store platelets didn't really stay in circulation. And this is a big problem for our patients who come back for prophylactic transfusions, because instead of coming back every 4 or 5 days, they need to come back every 1 or 2 days if they were to be transfused with cold store platelets. So currently, because of this cold store platelets not remaining in the circulation, we've transitioned most of our platelet storage to room temperature, which is 22 degrees under constant agitation. And now in Canada, we've allowed for 7 days, but like Nick was saying, in a lot of the European countries in the States, it's only up to 5 days. Now, there are also significant disadvantages associated with room temperature storage. So, one of the biggest ones is the short storage life, and you've heard from my colleagues that you can store the red cell for up to 35 to 42 days, and frozen plasma can be even stored for longer. So 7 days is really a logistic nightmare. And also, there are deterioration of quality, known as platelet storage lesion, which Nick has already touched on. And finally, it also encourages microorganism growth. Unfortunately, plasma is extremely nutritious, and microorganisms such as bacteria love to grow in them. So one of the reasons why we're interested in cold store platelets again is that the cold storage really reduces bacterial growth. And this is a paper published from colleagues in the States that show that you see the line flat on the bottom there, and that's the cold storage platelets versus the lines on top there, which are the room temperature store platelets. You can see that on the y-axis, it shows the different species of bacteria that are commonly found in our platelet products. You can see that the cold storage really mitigates that bacterial growth versus the room temperature store platelets, which have significantly encouraged bacterial growth. Now, if we put the platelets in the cold storage, we might be increasing the potential shelf life of the platelets. So in addition to the bacterial growth, the other reason why we are considering cold store platelets again is we've seen that there's actually a change and there's an increase in the need for therapeutic platelets. So this is data collected in a tertiary care hospital in the States back in 2009. What they did was they compiled the platelet utilization over the 3-month period. And what you can see here is I have circled it in red, is that most of our platelets have actually gone from being used for prophylactic purposes into being used for therapeutic purposes. So this means that they're being used to stop bleeding in an acute trauma situation. So you can see here that most of the platelets is actually being used for cardiothoracic surgery instead of used for prophylactic transfusion. So there is a question right now whether room temperature store platelets, because they were developed based on the prophylactic purposes, are they still the best for these patients who need immediate hemostatic efficiencies? So this question was asked even back in the 1970s, and we know that patients who have been transfused with cold store platelets, they have higher hemostatic functions. So this graph on the right here by Becker shows that the patients who have received cold store platelets, which are the dotted lines on the top there, labeled 4 degrees, they have better correction in bleeding time compared to patients who have received the room temperature store platelets. Now, so our research questions for today is that which platelet product is better for bleeding patients? So to answer these questions, we actually took up a model that is often used in trauma transfusion. So this model is called the massive transfusion protocol. So if a patient comes in with massive bleeding and recurrent bleeding, a lot of times what the trauma center will do is they will take three components that we normally store in Canadian Blood Services. So those are red cells, platelets, and plasma, and essentially trying to recreate the whole blood by combining these three components together. Now, in the clinic, this is done by taking one bag of each components, but in our experiment, we have actually just combined them in a 1-to-1-to-1 volume ratio. So there is a little bit of difference because the bags are not technically the same volume in clinic. However, so this is what we did. So we sampled the three components, and then we combined them into a transfusion package. So there are two packages you can see here. There is the warm and the cold. So the warm package is made from stored red cells, room temperature store platelets that are being stored for 1, 7, or 14 days, and then fresh frozen plasma. In the cold package, the packages are made from red cells and plasma, but with cold store platelets. We also simulated what will happen in a trauma situation by taking whole blood from a normal donor through phlebotomy. And then we have done two sort of different modification to make that into a trauma patient's blood. So the first one Dana alluded to is hemodilution. This is when the patient is transfused with crystalloid so that their blood is hemodiluted, their factors are diluted. So we did this by adding saline into the whole blood. We've also simulated a hyperfibrinolytic condition. So this is often happens in trauma patients where they experience an accelerated lysis of their clots. So this is done by adding tissue plasminogen activators into our whole blood. So we then added our transfusion package to these hemodiluted or hyperfibrinolytic whole blood, and then we ran the results on ROTEM. So Nick has talked a little bit about ROTEM and on how it works. So I'll be explaining a little bit more about what you're looking at. So essentially, when you run a ROTEM, you will be looking at a graph on the right there, and you can see that is a time-dependent graph. And there are a lot of factors you can actually derive from the graph, but the three main ones I'll be talking about today are the clot formation time. So that's the time it takes for the clot to go from 2 millimeters to 20 millimeters amplitude. So it's a time measurement. There's also the maximum clot firmness, which is the strongest your clot is during this test, and then maximum lysis, and that's how much your clot retracts during the time that this experiment is running. So looking at our data now, so I wrote on the title there INTEM. So INTEM is one of the activators that you need to add to get your ROTEM going. So INTEM is basically an intrinsic initiator, lactic acid. So I'll be walking you through the graph. So the graph is a little bit confusing, but I'll walk you through it slowly. So you can see on the graph first that there's three horizontal lines. So these are actually, the solid line represents the mean of the whole blood that we modified, but we didn't add any transfusion package. So this is your control baseline. And the two dashed lines are the one standard deviation plus or minus of the mean. So basically, that's our control. And then on the bar graphs are the results of the ROTEM after we added the transfusion package. So you can see here, first we're looking at the maximum clot firmness on the left-hand side there. You can see that after we add either the warm transfusion package or the cold transfusion package, either made from day 7 or day 14 stored platelets, you can see that we have massively improved the maximum clot firmness of the untransfused whole blood. There is a difference between warm and cold package, and we think this is due to the co-activated coagulation in the cold store platelets. So there's less active platelets platelet count in the cold store platelets. And on the right there, you can see that we're showing the data for the clot formation time. And you can see that the untransfused whole blood, they have very high, they take way longer to reach the clot formation time. And in our warm and cold transfused package whole blood, we're not seeing that. Okay, so this is the same experiment, but done with the extrinsic activator, which is XM, so, and it's tissue factor, basically. So we're looking at the same parameters again, the maximum clot firmness and the clot formation time. So you can see a very similar story there. So next we move on to the hyperfibrinolytic whole blood. So that was hemodilution. So now the whole blood has been modified with TPA. So these whole blood have strong hyperfibrinolytic properties. So when we did this experiment with our transfusion package again, we saw that there wasn't much of an improvement in the maximum clot firmness. So whether you add the warm or the cold, however, when we look at the maximum lysis, there was a significant reduction, but only in the cold package transfused whole blood. So this is significant on both day 7 and day 14. Now, when we ran the XM experiment with the same setup, similar story, not much change in the maximum clot firmness, but on the maximum lysis parameter, we saw this effect on day 14, but not day 7. So in conclusion, so day 14 cold sore platelets can still restore the hemostatic potential of bleeding patients, and the bleeding patients who receive cold sore platelets may have additional benefits of reduced clot lysis, which would be good because they're bleeding. And we're currently considering whether we could have cold sore platelets as an additional product to rheumatoid transfer platelets for these patients. Because I'm the last one speaking, so I can say we're happy to take any questions. Yeah, that's a good question. I can't tell you, but it's yes, I think so. Yeah, I was thinking of a mouse turn, but that's not the one that on the slide.
Just a really quick reminder for anyone in the room, please do use the microphone if you need to ask a question, just so the virtual audience can hear you. Thanks.
So we have a couple of questions in the chat box. Jim Bucell is asking, he said, many years ago, we identified aluminum in specialized blood products, factor concentrates, and IVIG. And he says, I apologize, I missed the beginning of the talk, but did you look at any particular types of specialized blood products for lead and mercury or aluminum? Narges?
No, unfortunately, we didn't look at aluminum. We looked at lead, mercury, and cadmium. That I didn't present cadmium.
Also a question here. Yeah, okay, thanks. There's also a question here that's addressed, I guess, to everyone, but it says, maybe I missed it, but are you also looking at red cell deformability in AIM-2?
That might be for me. Yes, that is the plan. We plan to look at red cell deformability with a couple different assays. So.
I guess this might be for you, Dana. Are there any plans to look at allowing people who were in the UK in the BSE years to donate? Because I would love to, but I can't.
No, we've absolutely been talking about that, and it has to clear Health Canada, which all of our referrals come down from Health Canada. So I think that now that I had a colleague who used to call the variant CJD outbreak the smallest epidemic that there's ever been in history, and so I think we had, I don't know, maybe like 120 blood donors who were affected. So I think that it's a reasonable request to make. People have to get on that. Okay, we have a question here from Dr. Stolla from the University of Washington. It says, great talks. Have you tried your new platelet storage bags for cold storage? And what would you predict will happen for activation and metabolism markers? That's for you, Nick.
as it stands, the reason that we haven't tried it is we're concerned about the rigidity of the bags. We want to see whether they would actually shake properly with the added polymer and whatnot. I would expect that they would follow the same trends. Like we would just see the same effective difference between the warm temperature and the cold. I think that it would follow very much with what we're seeing in the cold stored platelets. It hopefully would make a significant difference, especially in the cold. They'd like to aggregate a little more. So perhaps the polymer coating would prevent that. It's something that we want to do, absolutely. And I think in the next coming weeks, realistically, we're going to get into it. But as of now, that is the best I have.
Thanks very much, and thanks for the question, Moritz.
Maybe I'll just ask a quick one. So in the perfect world, if you find out somebody who has high levels of lead or high levels of mercury, what can you do? Is there a way to let them know? And what would they do about it?
Yeah, we're right now, so the CBS Ethics Review Board has decided that these are incidental findings. And so we've just written letters to the donors that have the very high levels to basically tell them to, go to your GP and figure out why you have these very high heavy metal levels in your blood. So we're our informant people. And we've also heard those people from blood letters. Right? So the heavy metal sources are really interesting. So we have a number of high lead donors in downtown Toronto. And it turns out that Toronto's never replaced the lead piping in the water supply. So, there's a high lead level in the So that's probably one possibility. We also have heavy metal levels that are high because people are living, as Narges said, within 80 kilometers of these big tailing ponds and smelters. And so that's
And for cadmium, like smoking is the biggest contributor.